Hi, this is Dr. S. Ravi Kumar, Associate Professor, Department of Electronics and Communication Engineering, St. Martin's Engineering College. Today, I am going to discuss about the topic microwave tubes and its classification, which will comes under microwave and optical communication. So, microwave tubes are the part of the microwave devices which will operate with the high frequency signals, means with microwave frequencies. They will operate at microwave frequencies. When microwave frequencies, as we know that they will be in the range of 1 gigahertz to, it will be in the range of 1 gigahertz to, it will be in the range of 300 gigahertz. So gigahertz, we know that it stands for 10 power 9 hertz, means it is a very high frequency signal. So when these microwaves are operating at these frequencies, when they are operating at these frequencies, the devices which are required for carrying these microwave frequencies should be very appropriate. So the electronic devices which are operating at these frequencies, they are becoming very small and they are unable to withstand these high frequencies. And as a reason, these microwave frequencies, when they are operated, when at the conventional tubes like pentodes, triodes, tetrodes, at these frequencies, they will come across different types of problems like inter-electrode capacitance, lead inductance, transit time effect, and gain bandwidth limitation. These are the problems which will arise when they are operating at the higher frequencies. So we will discuss about them in detail. What are those in detail? So these frequencies, when they are operated, they will be providing a very typical task for the conventional tubes. So that's why we will go with the microwave frequencies. So these interelectrode capacitance, coming to this interelectrode capacitance, we can see that Xc is varying with respect to the cutoff frequency Fc. That means as we are increasing the frequency, reactance will decrease. When the reactance is getting decreased in this device, you can see that there will be different capacitances will be increased, that is called as CGP, CGC and CPC. These are all the different capacitances which are occurring in this circuit. This type of capacitance is not at all required because this increased capacitance will decreases the voltage and it will also decrease the power. In turn, power will be decreased and the distance between the plates will also get decreased. As a reason, the total circuit will become short circuit and the circuit may also damage. So there is a remedy for that. What we can do is we can increase the distance between the plates. That is the one of the remedy what we can follow. And the next problem which will be occurring by the conventional tubes when they are operating at the micro frequencies are the lead inductance. We can see that this lead inductance is proportional to the frequency of operation. When the frequency is increasing, then inductive reactance is getting increased. As the inductive reactance is getting increased, the voltage at this inductive reactance will be less compared to that of the voltage existing at the base pins. So which will in turn increases the inductiveness of this circuit, which will make the circuit to have a more dissipation in the power. So as a result, this at conventional tubes, their lead inductance is also one problem which will be arising. And the next problem which will be coming is transit time effect. So the next transit time effect, what is transit time? Transit time is the time taken by the electron to travel from cathode to anode. The time which is taken by the electron to travel from cathode to anode is called the transit time. So generally this transit time should be lesser. at higher frequencies, because as the devices are operated at higher frequencies, they will expect the higher transit times. So as we see that if the voltage is given between the terminals, and this is the terminal between the cathode and the anode, if you take this cathode and the anode plate, when a voltage is applied between these two plates, and and this is the distance between the cathode and the anode, d is the distance between the cathode and the anode, and v naught is the velocity of the electrons which is moving from cathode to the anode. And when a permanent magnet is placed like this, what happens here? The transit time tau is given by the formula distance between the cathode and the anode to the velocity of the electron v naught, d by v naught, where we know that the static electric charge ev naught is equals to half the times of m into v naught square, where m is nothing but the mass of the electron and v naught is the velocity of the electron, and this v naught is the voltage which is given between the cathode and the anode. So from this formula we will calculate v naught, which is will be given by root over 2e v naught by m. This velocity, once it is calculated and it is substituted in this formula, where the transit time is given by d by root over 2e v naught by m. This is called the transit time. This transit time should be as less as possible for any device, but at higher frequencies conventional tubes cannot hold this, and they will have maximum transit time, and as a result conventional tubes fails to operate at higher frequencies. So coming to the next one, we can see that the devices which is having other problems like transit times, other than the transit times, we are also having the problems like skin depth loss, dielectric loss, and different types of losses which are occurring. So that we can also see the other limitation, which is called the gain bandwidth limitation. Generally, the gain bandwidth product always it should be equals to constant, but the gain should increase as the frequency is increasing. The gain should increase at a particular frequency. Gain will be maximum for any circuit. At a particular frequency, gain will be maximum. That is called the resonance, which is called the oscillation. At that oscillation state, gain should be maximum. But for the conventional tubes, because of this inductiveness which is there, inductive lead inductance which is increasing, which will result in the decrease in the gain at a particular operating frequencies, which is not at all useful. So that's why the lead inductance affect the gain bandwidth limitation will be having a problem when you are operating at the lower frequencies. So the next thing is the losses which will be occurring is skin effect loss, that is skin depth. At higher frequencies, these electrons will be staggering on the surface of the device. They are not penetrating into the device. That is causing the I square R losses. So, and the next one is dielectric loss. Dielectric substrate, because of the dielectric substrate of the conventional conventional tubes at microwave frequencies, there will be other type of loss which is occurring called the dielectric loss. And radiation at a higher frequencies, radiations will be because these devices lower frequency devices cannot withstand these higher frequencies, they will be prone to more radiation. So that is called, which will cause the radiation loss. So these are the different types of losses. Now coming to the classification of the microwave tubes, they are classified as linear beam tubes and crossed field tubes. That linear beam tube is called as linear beam tube is the O-type tube, and crossed field tube is called the M-type tube. I will now show the classification here. What is the difference between the O-type tube and the M-type tube? So Microwave tubes, they are classified as O type and M type. O type means original type. O stands for original type and M stands for crossed field type. Crossed field type. So original type means where all electrons which are moving will be linearly varying with respect to the magnetic field. If the magnetic field is applied, both electrons and the magnetic field, they will be moving linearly. Whereas in the M-type tubes, electric field and magnetic field always perpendicular to each other. Coming to E and H, if it is EX, it is HY. If it is HX, if it is HX, it is EY. So like that, so there will be divided as O type and M type. So coming to this classification, we will see in the slide how they are classified. So this linear beam tube, which is called as the original type tube, they are divided based on its cavity and they are also divided based on a slow wave structure. So the devices which are based on the cavity are called the klystron, which is in turn they are divided as reflex klystron and two cavity klystron. And based on the slow wave structure, they are classified into two categories. They are forward wave and backward wave. Forward wave means the electromagnetic wave movement will be in the forward direction, whereas backward wave means the movement will be in the reverse direction. So the devices which will be studied and in this category are reflex klystron and another one is two cavity klystron. Reflex klystron is an oscillator which will operate with a single cavity, whereas two cavity klystron is an amplifier which will be operating on the with the two cavities. So cavity is nothing but a hollow structure which will be used for make electrons to be interacted, where electrons will be interacted, and this other types of tubes are called as M-type tubes. They are called the crossed field tubes. Crossed field tubes, in this field, I already told, the electric field and magnetic field will be always perpendicular to each other. So again in crossed field tubes, there are two types are there. One is resonant type, non-resonant type, and which are depending upon the major principle, which is called the microwave amplification by stimulated emission of radiation. So resonant type means which will be depending upon the resonance, that is on the oscillation, and non-resonant type means the devices which are not depending upon the oscillations, and major means which is depending on the major effect. Those devices are called the major devices. So this forward type of devices, they are the devices which will be studied under this full wave continuous frequency amplitron, dematron, and backward wave structures. They are reentrant type and non-reentrant type. Again, reentrant means, the meaning of reentrant means where inductance is nullified. The device which will make the inductance nullified, that device is called as the reentrant type device. That device which is used with this principle is called the amplitron, and the other device which is called the, which is a non-reentrant type, that is called the calcinotron. So these are all the different devices which will be depending upon these principles. So so the next one is maser. So with the principle which is depending on the device which is depending on this principle is called the gyrotron. So the next principle what we will see is we will study about the O-type tubes, which is called the linear beam tubes. So linear beam tubes, you can see here the circuit classification here. It will have the cathode and a collector. It can be an anode or a negative repel collector which can be used. So cathode will be placed here and it's an RF circuit. It can be a RF circuit, and electron beam will be transmitting in this space, which is called the interaction space. This is called the interaction space, where RF input is given from one side, and RF output will be collected through coaxial cables or connectors. By using the connectors, we can collect the RF circuit. So types of linear beam tubes already we discussed. So which will be using the tubes which will be using the electromagnetic cavity type. Another one is which will use the slow wave. The devices which will be using the cavity type, there are two reflex klystron and two cavity klystron. And the devices which will be operating with the slow wave structure is called the helix traveling wave tube. So this is the typical diagram of the representation of the two cavity klystron, where two cavity klystron, you can see here, it is having two cavities. One is called the buncher cavity and the second one is called the catcher cavity, where this is the relay, this is cathode and this is anode. There will be two polarities, cathode and the anode, and the electrons will start traveling from cathode to anode. And once the power supply is given from negative, cathode is connected with negative and anode is connected with positive terminals. Once this is called the electron gun. Electron gun will be continuously pumping the electrons. They will continuously pumping the electrons, and RF input, where the electromagnetic signal which should be interacted with this electrons will be pumped through this cavity. So once these electrons will enter into this cavity, they will interact for the first time in the buncher cavity, and the electrons, once it reaches into the catcher cavity, radio frequency signal, again it will interact with the radio frequency signal for the second time. In this process, in this two cavity klystron amplifier, the process which will occur is called the velocity modulation. Velocity modulation, where all the electrons which are pumped from this electron gun, they will come across with a particular modulation technique called the velocity modulation, where we will take three electrons. One is called the early electron, reference electron and the late electron. So I will show how they will interact in this free space, these electrons, and these electrons will be interacted in a space called as drift space. That space is called the drift space. So as we are seeing that there are three electrons which are called the reference electron, late electron and early electron. We will consider these three electrons as V0, that is VR, VE and VL, which is called the late electron. Reference electron will travel with a velocity V0 equals to root over 2e V0 by m. This is called the initial velocity of the electron. So as the electron enters into the buncher cavity, when it is entering into the buncher cavity, this electron will have this initial velocity. That electron will have the initial velocity. And there is another electron which is called the late electron, which will be starting after this initial velocity of the electron, that is called the late electron. That late electron will have the velocity V0 equals to root over 2e V0 minus Vm sin omega t by m. 2e V0 minus Vm sin omega t by m. And there is an early electron which is moving faster. It should be deaccelerated because it is moving with the more velocity. So it should be deaccelerated. So for that electron, that this velocity will be given. And there is a late electron that is moving later than this reference electron, which is having the low velocity. It should be accelerated. So for that electron, we will give the velocity which is equal to root over 2e V0 plus Vm sin omega t plus m. This type of velocity modulation will be used in the two cavity klystron, where this electron, once it enters into this buncher cavity, here you can this electron will be entering into the buncher cavity. This is called the buncher cavity, and they will be moving like this in a linear fashion, where electrons will be moving in the direction of the magnetic field, and these electrons, which will be called the previously electron is reference electron, early electron, and late electron. These three electrons which are moving in their own velocity. Now these three electrons are made to travel together, and they are made as a bunch. They will be made as a bunch, and this bunch of electrons will be, for the second time, it will be traveling into the cavity which is called the catcher cavity, where you will take the RF output. When here you will give the RF input. RF input will be given. So this space where existing between these two cavities, this is called the drift space. Drift space. So in this drift space, electrons will be bunched together and they will be traveling. This process will be used for amplification in the two cavity klystron. So coming to this other reflex klystron, and the other topic what we are going to discuss is called the reflex klystron. So reflex klystron. So the next topic is the internally it will be shown like this. In two cavity klystron, you will have two cavities. Whatever the cavities I have discussed, these are the two cavities, and this is the RF input, and the buncher cavity. This is called the buncher cavity, and this is the catcher cavity, which I shown on the noteboard, where the electrons will be moving this phase, and they will be bunched together, and these electrons will be traveling, and this is called the drift space. So coming to this, in the same way, you will have the structure of the reflex klystron. Reflex klystron is a single cavity oscillator, where microwave tubes can be used either as an amplifier or an oscillator. The previous one what I discussed is called the amplifier, and here it is an oscillator. In reflex klystron, only one cavity is used for both bunching as well as catching. So here also the same principle will happen, but what happens here is the electrons will be repelled back into this cavity for the second time. Three electrons will be traveling. The first electron will be repelled first, second electron will be repelled next, and the third, which will be unable to move into the repelled space, will meet with these electrons in the cavity for the second time. So all these electrons will meet into the cavity for the second time in the same cavity. So you can see the structure of the magnetron like this. So now I will show the M-type tubes. So coming to the M-type tubes, this is the slow wave structure, helix traveling wave tube. I already told you another tube is there with O type category. This is the helical tube. Helical tube will have the slow wave structure, where the electrons will be slowed down in this structure, whereas in the tube type structure, where electrons will be slowed down by the modulation process, but through the structure only the electrons will be slowed down in this process, where you can see the circumference and pitch of the helix will be calculated, and these will be used for amplification process, and helix traveling wave tube is an amplifier. And coming to this magnetron, this is the cylindrical magnetron. This is called the crossed field tube. And the second category type tube, which is the M-type tube, which is a crossed field tube, which I will show in video clearly how it will be used. It will be having an 8 cavity magnetron, where it will be having a cathode and the anode. This is called the anode slab, and this is the cathode slab surrounded by the 8 anodes.